So now in this video we'll look at 1A, restricting the domain. So I'm not going to go through the points here in the blue box. If you need to pause the video now and have another read of have a read of what's there, then that's fine, do that. But you will find that most of that I've covered previously. This notation you may not have seen before, but it's just saying if the inverse relation is a function, and you know what that means, and you know that some functions, their inverse won't be a function, but if their inverse is a function, the inverse function is written as f to the minus 1 of x, then if we combine if we take the inverse of a function, we'll get x. Likewise, if we take the function of the inverse, we will get x. Now you'll see that actually in action with some functions. If the inverse is not a function, the domain of the original function can be restricted and you can create a function, an inverse function. So let's have a look at some examples. So the first example, consider the function f of x is 3x plus 2 and g of x is 1/3 x minus 2. Now they've been deliberately chosen because it's possible to show that this g of x is the inverse of f of x. Now, there's a couple of ways you can do that. We saw in the blue box, it's not going to go back, we saw that if you take the inverse of the function, then you should get x. So we could actually do that, or we could take the function of the inverse, either one of those, and if we produce just x, then we know that these two functions, f and g, as they're stated there, and keep in mind that g of x could have been written as, well, we're going to show that it could be written as f inverse function of x, or we could just start with f of x, go through the process of swapping the x and y, replace f of x with y, go through the process of swapping and show that you create this. I'm going to do it both ways for you. So, started with f of x, replaced f of x with y, swapped the x and the y, made y the subject, replaced that y with the appropriate notation, which is inverse, because this function y I've created through the inverse process, and we get this 1/3 x minus 2, which is actually g of x. So that's one way to do it. The other, we're going to take f of g of x, f of this. So the f function is 3 times normally the x, but I'm going to put g of x in the spot for x. So in this spot for x, I'm going to put all of this. So it's 1/3 x minus 2. And what do we do for the rest of our function? We add 2. So this g of x had to get multiplied by 3 and then add 2. So 3 times 1/3 is 1, expanding in the bracket, and you're just left with x minus 2, and then we've got a plus 2, and so it's possible to show that f of g of x is actually x, therefore f of x and gx are inverse functions. I've done this one, f of g of x, I've just done that one there. Let's do g of f of x. So g of x is to take 1/3 and put x, and x has to be the f of x expression, and f of x is 3x plus 2. So I've got 1/3, my new x, 3x plus 2, minus 2, which is 1/3, 3x, which is just x. So again, just showing that they are inverse functions. And in example 2, we're going to actually see this process of restricting the domain in action so that we get an inverse function. So considering the function g of x equals x squared plus 2, so I think that graphing here is going to be really helpful. G of x is x squared plus 2. Normally you would consider your parabola and add 2 to it, so it pushes it up, so it sits there like that. However, we're only going to consider this original function when x is greater than or equal to 0. So we've got this situation, and if that is 2, then we've got the graph going up there. Now, it says find g inverse of x and identify its domain and range. Let's identify the domain and range for the original function first. So the domain is x less than or equal to 0, and the range is y values greater than or equal to 2. Okay, let's go straight into finding the inverse. So we're going to replace this with a y just so we can do the swap. Now we're creating the inverse now. X goes here, y squared goes there. We've created the inverse in that line. We make y the subject because we write our equations in terms of y, and we take the square root of both sides to make y the subject, square root of x minus 2. Now, things we know, and that becomes, therefore, g inverse of x becomes square root x minus 2. It's too confusing to leave it as y because we talked about a y there, and this is actually a very different y to that one because remember we swapped them. This is the inverse function y. So let's call it the inverse of the function. It's taking the square root. We know that you can only take the square root of a positive number. So for this under here to be a positive number, x has to be greater than 2. So we've got the domain of this inverse function is x must be greater than or equal to 2. See the connection? Domain of range of 1 becomes the domain of the inverse. Let's draw that. So, like I said, graphing that, when x is 0, the graph doesn't exist. When x is 0, up and down here, because we're trying to take the square root of negative 2, it doesn't exist until we get to x is 2, and 2 subtract 2 is 0, square root of 0 is 0. I think the next value that's easiest to identify is when x is 6, the square root of 6 minus 2, which is 4, square root of 4 is 2. So when we get to 6, we've got 2. When you put actual x equal to 4 in there, you get root 2, which is a number between 1 and 2. So we're actually getting this graph. Now, we can see that the domain is only the x value is greater than or equal to 2. But if we did it for long enough, we would get an ever-increasing y value, and so we would get that its range would be y greater than or equal to 0. Now, remember we had domain was greater than or equal to 0, and now we've got the range in the inverse is greater than or equal to 0. And that works each time. The domain of the original function becomes the range of the inverse. The range of the original function becomes the domain of the inverse. And if I was to draw it a little more accurately here, I'd end up with a function looking a bit like that. And if we put our y equals x in, we can see that that and that are equal distances. And then we go from here to here, cutting through and so on. I think that's about it. Do you notice, you will notice that I didn't do a you do. Could you please make sure you add that to your notes? I think all the questions from 2 to 8 are important because they're fairly straightforward, very good practice at all of this. Then I just chose a few, and you can do more if you have the time. Please take it slowly. It's a very important concepts to master, both algebraically, doing the swap, and graphically,